Welcome again to Let's Talk Advanced Chemistry, Chemistry 2, Pastor Dan. We are looking at something called, up here it says van der Waal equation. Now, van der Waal equation, we started with the ideal gas equation, idea how a gas operates in an ideal or perfect sense. Now, van der Waal was a scientist who decided, let's see how to tweak that ideal gas equation in order to make it real world. Actual interactions, the electromagnetic effect of the different process between it, the collision interactions, all those kinds of things are taking an effect inside. What I'm trying to say here is the kinetic theory, those assumptions we make, the van der Waal negates those and makes it in a proper sense. The van der Waal. So the definition of van der Waal equation is it's a relationship of a gas in a real world conditions. And the equation here, and then just all this is just taking this equation and plugging it in. We know what P is, we know N is moles, R is a gas law constant, 0.0821, liters, atmospheres, 1 mole Kelvin. That's the only we're going to use because of the values we had. T is temperature, V is volume. B is a constant and A is a constant. Now these constants are found inside of here. So it depends on which gas we're talking about. If it's helium, it's these conditions. If it's neon, argon, krypton, those common gases left are there. So let's do a problem. Calculate the pressure of 36.223 liters of oxygen at 21.72 degrees Celsius if there's 47.225 grams of gas. Compare the results of the ideal gas expression in the same problem. All right, so we need to go back and look at oxygen. So there's my A value and there's my B value for oxygen. So what we're going to do is we're going to take our equation, and first of all, I got to convert to moles. Remember, oxygen is diatomic, so it's 32 grams of 1 mole. So we have 1.47573 moles of oxygen. Now we're going to plug those values in. We're going to use the 0.0821, not 8.31 liters kilopascals, because both of the A and B value are in atmospheres. All right, so put our values in there. It's a little small. Let me make that a little bigger for you. I'm not going to do that because it messed up last time I tried it. So you can see a little bit better on that. There we go. And what we're going to do then is just plug that in when we do all of that stuff. So you can take 1.47573 times 0.0821 times 294.72. Of course, that's the temperature here in Kelvin at 273. Hit equal. Divide by 36.223 parentheses minus 1.47573 times 0.038. My moles cross out. My Kelvins cross out. My liters cross out. I'm just left with atmospheres. Hit equal, get a number, and then do this one over here separately. 1.4573 moles squared times 1.36. Divide by 36.2. When we do that, we get an answer 0.98479 atmospheres. Now, let's compare that to what that would be at ideally. So we take in our equation here, PV equals nRT. Oh, that's it constantly wants to mess with me here. Oh. And we plug our values in. And when we do, we get an answer 0.98577 atmospheres. Now you can see the numbers are relatively close. It's not perfect, but the reality is what we're doing is getting it as close to that value as we can. All righty. So the question is how accurate do you want? This number is not that far off. This is a lot easier to calculate. That's why we often use ideal. But this value right here is the more accurate number because of intermolecular forces, collisions, molecular forces, things along that line. So let's try another one. This time, find the pressure of 40.22 liters of nitrogen at 35.7 degrees Celsius if there's 3.1115 moles of gas. I'm going to give you the moles Make life easier, compare the result of the ideal gas expression to the same problem. Now, you don't have to do that. It's just nice to see, to be able to compare. All right, so take our equation, and if we look at our chart again, we're looking at oxygen, I think it is. Nitrogen, there it is. So nitrogen, A value 1.39, B value 0.0391. Take and plug our values in like such. When we do that, first equation, we get a number of 1.967. Second equation, get a value of 0.008319. Last fill column, 3 decimal places, an answer of 1.959 atmospheres. If we apply and solve for P, ideally, the answer comes out to be 1.961 atmospheres. You see there's a slight derivation, the interaction between molecules, collisions, reflections, all those kinds of things. All right, that's it. Hopefully not too bad. Take care. God bless. Bye.